16.4 Green's theorem. We will continue the discussion of the line integral from last time. We mentioned there is a theorem called a Green theorem that shows that if for given given field we have a Qx equals Py, then we have a potential field. And today we will show the theorem. The theorem says if you have a line integral over a closed region that's called D, and the curve around it is called C, and this C must be counterclockwise for the theorem to hold. Otherwise, if it's the other way around, then the theorem would have a negative sign. So the theorem says if you have a field that's called PQ, right, then if you integrate this field along the closed curve, okay, let me put an arrow here to represent it's counterclockwise. Then this must be the same as the 2D integral of Qx minus Py over this domain enclosed by this C. And you can see if the C is the other way around, like that, then the left-hand side would be the negative of the right-hand side, right? So let's stick to the counterclockwise direction. And let's prove it. Okay, let me just erase this part so we don't need it. Oops, alright. Let's write on the left-hand side as P dx plus Q dy. And if you compare the both sides, you will see there are P parts and Q parts. So they are actually two independent and not two different theorems. One is this Q dy equals Qx dA, and the other is P dx equals negative Py integrated. Right, so we will prove them one by one, and then add together we get the Green theorem. So let's go back to the first part. Suppose you have a contour like that, and let's say, how do we write down the integration on the right hand side? Since we are going to have dy, so let's put dy on the outside. So let's say it's from C to D. So it's from C to D, right? Then I can cut it into a left part and the right part. So I cut into a lot of horizontal segments like that. So this one is called H1 Y and H2 Y. So this will be from H1Y to H2Y. You know, that's x equals. So they have dx, and then have qx integrated, right? Then we will apply the fundamental theorem of calculus. This part, it's integration of a derivative. So it's just the q of the right end, which is x, not x, because x is a given function of y, is 2, and y minus the left hand. right? That's the integral. Then integrate over what? Over dy. Okay, now you divide the curve C into two parts. This part and that part. And let's call them, sorry. Oops, I keep doing that. Sorry for that. Let me call this C1 and call this C2. Right. So this one can be written as C1 Q dy, because along C1 the coordinate is just this, right? Then minus along C2 Q dy, because along C2 the coordinate is given by, oops, I think this should be called C2 and this is C1. Okay, so this is C2, this is C1. So along C2 it's H2, along C1 it's H1. And because our dy is always positive for the area integral, so C1 and C2 both go from bottom to the top, right? Okay, so this is Q dy. And then if you combine them, you can see C2 is go from bottom to top, and the C1 is from bottom to top, but it's a negative sign, so it's, if you reverse it, it becomes like that, or you can just say it's our C, right? Because C2 followed by negative C1, that's exactly a counterclockwise integral. So that's our proof. See, we showed that the left hand side equals the right hand side, which is what we claimed, right? Now let's see the similar thing for the for the p. So what do we want to prove? We want to prove this. Let me just take a look. So py integrated equals negative p dx. Okay, so p dA. So eventually it will be a negative integral of p. Okay. So this time we were cutting to a vertical slab, like that. Let's just assume it's from A to B. So you will have, let's say this is a g2 of x, and this is g1 of x, and then you can plug in here, and this is p, sorry, that's p, this should be py times dy dx, then this part becomes ab, and this is p of top minus p at bottom, g1 x. Right, then as before we will call the top part C2 and bottom part C1. C2, C1. So, and this is C2, and that's p dx. And to make dx positive, we have to go from this way, right? And C2 also this way. So you have that minus C1 p dx, and if you put them together, then you get C2 minus C1. And what is C2 minus C1? It means you do this way, then followed by negative C1. So that's your loop. But that loop is clockwise. So it means it's negative counterclockwise. So here's the proof. Alright. So now we have proved the green theorem. And the green theorem can tell us quite a few things. First of all, it proves our theorem about the gradient field. Green theorem shows that Py equals Qx implies let's see where it is. Okay, Py equals Qx equals the integral is 0 on the right side and on the left side. So it means the flux. It means the line integral, or the vector line integral, is over a closed loop is always 0. Right? Closed loop is always 0, and that means potential field. Great, that's what we claimed last time, right? Now the proof is complete. Second, the green theorem has some very interesting application. Suppose I give you a domain, I give you a curve, I ask you what is area. It turned out that you can just use the boundary curve to find out the area. Here's the theorem. The area is just equal to the boundary integral in this simple form. You integrate x, then x times dy, and over a counterclockwise direction. And why is that? Let's look at our green theorem. If you plug in if you plug in this part, okay, use this part. If you plug in q equals x, then you get the left hand side. And what's the right hand side? Qx equals 1. So that's the area. So x dy integrated give you 1 and give you area, right? And similarly, if you plug in y to p, what do you get? You get a negative area on the right hand side. So you get a y dx with negative integral. Negative. Like that. And you can even combine them. You can add the right hand side together, then divide by 2. Because they're both a, right? The x dy minus dx. Well, you may say, why bother doing this? Well, that's because sometimes the last integral turns out to be the easiest one. For example, let's take a look at let's say the ellipse. Alright, what's the area inside an ellipse? Okay, let's say this is A, this is B. Then we know the equation for ellipse is this. Right? So let's parameterize this ellipse. And I believe you have seen this before. X equals a cosine theta, y equals b sine theta, because if you plug into this formula, you will see cosine squared plus sine squared equals 1. And the theta goes from 0 to 2 pi. Right? So let's find out the area. And let's use the last formula there. 1/2 and x dy, so let's plug in x, a cosine theta, and dy is d of b sine theta minus y d of x, alright, over this counterclockwise loop. Okay, so A cosine theta. And what is this? The theta is our variable, so it's B cosine theta d theta. Minus B sine theta, A sine theta with a negative sign, right? D theta. And then put together, you see that? Cosine, cosine, sine, sine. So it's nothing but AB d theta. And the theta is from 0 to 2 pi. So it's just AB times 2 pi, then divided by 2. So it's pi AB. Done. So the area of a ellipse is just pi times A times V. And you can see this integral is particularly simple because we have this cosine squared plus sine squared equals 1, right? If you only use half of that, well, of course, you can still get the same result, but then you have to use the double angle formula, right? So we can use either the first one or the second one or the third one to get your area. And it can also be used to find out area of a polygon, but we will not do it here. Now let's see a third application of this green theorem. It can be used to find out an integral of a vector field along a closed curve. Well, in last example, we see that the integral along a curve is can give us the area, but sometimes the integral along a curve is not so easy. It turned out that the integration along in the domain is easier. So sometimes we use it the other way around. We write down this as the domain integral. So we compute the right-hand side to get your left-hand side. Let's see our example. But be careful, C has to be counterclockwise. So if C is not counterclockwise, we have to flip the sign on the right-hand side. All right, let's see this one. Let's say you have a counterclockwise curve. You want to integrate this. And what is this C? C is a path go from origin to 1, 0, then to 0, 1, then back to origin. And you can check it's indeed counterclockwise, right? So, well, if this field happens to be a conservative field or potential field, then you know the result has to be 0, right? Because the loop integral of a conservative field is 0. But even if it's not 0, we can still use green theorem. Let's see what I have. If you do it, change the domain, then domain, of course, is just this triangle, right? Then let's see what's inside the domain. You have qx, which is negative y, and py is nothing, so it's just negative y, right? And dA is just the dx dy, or if you like, let's say dy dx. So x is from 0 to 1. Then for each x, y is from 0 to x, right? Yeah, it's from 0 to x. So then integrate, that's pretty easy. You get negative y squared over 2 from 0 to x. Then you get negative x squared over 2. So you get negative x cubed over 6. And then you get negative 1/6. Okay. If you do it directly, let's see what you get. Well, it's not too hard because two of the segments are horizontal or vertical. But let's see. So if you do it directly, then you have to cut this into C1, C2, and C3. C3 is downward. Right, so let's see. C1, you have x to the fourth dx plus xy dy. Right? Then you plus the integration along C2 and along C3. Right? So along C1, what do you have? dy equals 0 because it's horizontal. So just x fourth dx from 0 to 1. And C2 is hardest because along C2, y equals x. Oh, y not equal to x. Y equals 1 minus x. So dy equals negative dx. Right, like that. And x goes from 1 to 0. The last part, along C3, dx equals 0. So you only have dy. And then y goes from 1 to 0. But actually this term is gone because along C3 x equals 0, so that's 0. So everything is 0. Okay, so let's see the first term. Then you have x to the fifth over 5 plus, and this will give you x to the fifth over 5 minus x squared over y, sorry, x squared over 2 times y. Oh, that's hard because I have to plug in y. What is y? Y is 1 minus x, right? So it's actually more complicated than that. So you get minus x, then plus x squared, right? Then you integrate, then you plug in the limits. And you can see this part cancel that part because it's from 0 to 1 and 1 to 0. So you just plug in 0, you get nothing. 1, you get, because it's in denominator, down there, so negative 1/2 plus 1/3, and that's negative 1/6. So flip it, get, and change it, sign 1/6. Oh, wait. Which one is correct? This is a 1/6. And then that one is, let me see, okay. So qx equals, oh, sorry, qx is just y. There's no negative sign, right? Qx equals y. So there is no negative sign. So this is a plus. So it's actually it's plus. Okay, plus. Everything's plus. Okay, so it's part of 1/6. Okay, but anyway, the idea is you can use the Green's theorem to change to a double integral, and sometimes, for example here, the double integral could be easier, right? Okay, let's see one more example. Let's say you have a double integral, no, not double integral, line integral, and this time it's y plus e to the square root of x dx plus 2x plus cosine y square, like that, dy, and then you have this c is between these two curves. So if you plot it, you will see a parabola and the other parabola like that. That's the c, right? and C is counterclockwise, so C is like that. And this is 1, 1. So if you do integrate directly, then you have to do C1 and C2, which is a bit hard. So let's try to change to the double integral. So it's counterclockwise, so we can write down this domain directly. Right. So let's do it correctly this time. Qx. What is Qx? Oh, that's really easy. And what is Py? It's also easy. Oh, it's just 1. Oh, it's just area, right? So what's the area of this? So that's really nice. So you can just find out the, let's say dx dy, and x is from 0 to 1, and y is from the lower one. What's this one? Y equals x squared. Right? And the other one is y equals root x. So x squared to root x. And then you have 0 to 1 root x minus x squared. Right? And then you have x to the 3 halves times 2/3 minus x cubed over 3. Then plugging the limits, you get 2/3 minus 1/3. Is that correct? Yeah, seems correct. 1/3. Right? 3 halves, 2/3. 2 becomes 1/3. Okay, so you got the answer pretty easy, right? It's much easier than have to handle all of that. So that's how we apply Green theorem. Okay, let me mention one more thing. What if the domain had a hole? Region with hole. Suppose you want to integrate a curve PQ like that curve here. But in the theorem we mentioned earlier, we need to cut this into a lot of vertical or horizontal slices, right? But now, if there's a hole in the middle, they cannot do that because, okay, by the hole I mean in this region, P, Q, undefined. Well, you may say it's undefined. How can we do it? Well, even if it's undefined in this region, in this shaded area, but along the curve C, it's defined. So this integral is still well defined. It's just that the Green theorem does not apply directly, right? Because Green theorem must contain everything inside C. So if you have to allow a hole there, then we have to cut this domain into this way. Put a line here and do this. You trace this C, then you go there and go along this and backward. So it's like you're forming a path inside, then along it, then back, and like that. Okay. So you can see this path will enclose the domain D, with that hole. And this part, it contains this and that. Actually, it's on the same exact path. So they will cancel. The integration along this and that will cancel. So you can call the outside one C and inside one C2. Let's call this C1. So you can see this C1 and this C2, the C2 is going the other way, right? You see that? It's going clockwise. So if you also call it counterclockwise C2, then this is actually minus C2. And then that equals the domain integration over this domain, qx minus qy. So if your domain D has a hole, then the boundary of D is C1, the exterior one, and negative C2, the interior one. So the interior boundary is negative, or you can say it's clockwise. Okay? And that's an extension of the Green theorem to a domain with a hole. And that has a very interesting implication. F equals a particular field in 2D, x over x squared plus y squared. This is a very special field because you can check its qx and the py. You will see they are actually the same, but not always. Let's take its x derivative. So let's do the product quotient rule. So top derivative is x, the bottom is x squared plus y squared, and minus the top and 2x squared, like that, right? Which means y squared minus x squared plus y squared, and that's the qx part. And let's see what py. Py is negative sign, then have x squared plus y squared, then top is y prime, which is 1, and times that, minus y, you keep it there, then you have 2y squared, so you get negative x squared minus y squared, and they're the same, right, because of negative sign. So it means qx equals py, however, not everywhere. Where did it fail? Only at one point, when the denominator is 0, which means origin. So you can say that's only one point, but that one point will change this completely. So if you integrate that field along the curve, say this is center and this is origin, this is the radius 1, you see. If you are not careful, then you may say, hey, this must be 0 by Green theorem because this is true, right? Well, except at one point. But if you do it directly, you will see what it is. So let's just do it. What is it? Negative y over, and then we can call it r squared, right? And we call it 3x. Here plus x and r squared dy. Right, then let's say I use theta, right? Then it's negative, y equals sine theta, and I equals 1. Then you have d of cosine theta plus cosine theta, d of sine theta, and from 0 to 2 pi. Right, let's see what I have. D of cosine theta equals sine theta d theta. It's sine theta square plus this will give you cosine theta square d theta, 0 to 2 pi, and that is 1, so it's 2 pi. And this certainly is not 0. So this does not mean the Green theorem fails, because Green theorem says it must be 0 everywhere. I mean, this must be satisfied everywhere, but now it failed at this particular point. Well, but this gives us something although it's non-zero, but this is a universal constant. Let me show you why. Suppose you have another whatever domain, so whatever curve, let's call it C. I claim the integration along this C, not necessarily that circle. Okay, anything contains the origin. Okay, C contains the origin. Then this integration is also 2 pi. Why is that? Well, let's see. If we call this domain D, right? Then do you remember that theorem? It says the integral over this domain is equal to the difference between the two integrals, the outer one and the inner one. Now, what is qx minus py? It's 0 in this domain, right? Because this domain does not include the origin. So, if that is 0, if this is 0, then it means integration along C1 and C2 are the same. And we know integration along C1 is 2 pi. So how about integration along C2, which in this case is just called C, that's also 2 pi. So we have this wonderful result. It says for this integral, this particular field, the integration along any path including the origin is 2 pi. On the other hand, if it's not including the origin, then it's 0. Because, it's in a domain that contains only points where this condition is satisfied. Right? So by Green theorem, it's 0. So the Green theorem can have some very fancy applications. Okay. And I think that's it for this chapter, for this section. We'll continue next time.